So in this session, we're going to be discussing a new solution called Cisco's Field Area Network Solution, and specifically a technology called Cisco Resilient Mesh for industrial IoT market. So basically, in the IoT group, our basic charter is to take IT architectures but apply them to OT use cases. So we're looking at, when we say industrial IoT, we're looking at manufacturing, transportation, smart grid utility space, mining, smart cities, transportation systems. And what we did, we launched our Field Area Network solution in 2012. This has been shipping for about 5 years now. And our initial focus was the smart grid utility space. So this presentation is going to describe use cases in the utility industry and with a solution that we've built for this. So the reason why, go ahead, Yev. The reason why why we entered this space is that vendors have been building wireless mesh networks for the utility space for several decades. The reason why we entered the market is that we saw the industry was transforming from proprietary single protocol use cases, single application use cases, more towards multi-service architectures based on that need more interoperability and enterprise class security and much more resilient communications, high availability. So you can expand across a wider range of use cases within the utility grid. So we introduced Cisco Resilient Mesh. We've had this mesh in production for about 5 years now, and to date we've connected over 5 million smart meters in the US and North American market. So the characteristics of this Resilient Mesh, it's a high performance RF mesh network. It's a rate adapts between different data rates with a high data rate of 1.2 megabits per second, going down to 50 kilobits per second. And we have adaptive modulation to be able to change that dynamically in the field because you'll get different distances and different received signal strengths based on the different data rates. So this is the unlicensed spectrum. This is 902 to 928 unlicensed bands, and we do frequency hopping within 64 channels within that band. So that's available throughout the Americas, most of Asia. And then there's 800 megahertz available for Europe, Middle East, Africa, India. So this is a high-performance mesh in terms of driving lower latency, because we're now moving from monitoring use cases to control. One of the key things in the utility industry, they're seeing a lot more penetration of renewable energy, and we're starting to see the impact of intermittent power supplies destabilizing a lot of the grid. So the utilities need a much higher performance wireless sensor network to be able to monitor and control how power flows through the grid. So in this Resilient Mesh, we've been able to optimize performance to get down to 14 milliseconds per hop latency. So now, again, there are different recloser schemes. You can reroute power through the grid in very short time periods.
So with 800 and 900 megahertz, you can have pretty good distance between mesh nodes, and you don't have as much interference with.
Exactly. This is a mesh network, so every sensor is a repeater in the network, right? And so the link distance will vary dramatically based on data rate as well as the physical topology. So on average, we see, like the networks we've been deploying today for smart metering is roughly 150 kilobits per second. Mm-hmm. The average distance is a few kilometers, about a mile between hops. But in urban environments, that's going to get much shorter. Right. But in rural environments, that'll grow more than a mile.
Right. So I think just because mesh networking is sort of, people may not understand what that really means. It might be useful if you just give like a 30-second elevator pitch of what mesh networking actually means.
Right.
Yeah, so maybe I should just skip through.
Mm-hmm. All right, if you're going to do that later, then just ignore me.
Yeah, that was. Yeah, this is, yep, go ahead.
So let's talk about a little bit, what is mesh networks or what is FAN, right? Mm-hmm. So let me zoom back here. So what you're seeing here is a typical grid, so you have the generation and transmission carrying the power to the substations. And from the substation onwards, you have the distribution side of the grid. And on the distribution grid, you have a variety of grid devices for monitoring and control of the grid. So things like voltage regulators, recloser controls, capacitor banks. But you also have devices, on-prem, for residential or commercial customers, like the meters for usage and billing, right? You have, for industrial customers, you may have demand meters and demand response. But there's new types of devices coming on the grid, distribution grid. Things like rooftop solar, microgrids being integrated into the utilities grid infrastructure. So the fan is basically, when you enable these devices, grid devices with communications capability, basically, with these radios, mesh radios that are running on the ISM band, they mesh together, and we'll go through the protocols a little bit, but basically, the devices form the mesh, and the field area network router essentially is the aggregation router to connect the devices over WAN to the grid operations, right? So the scope of FAN is really not on the transmission side. Let me just put it that way, right? It's the field area side of it. And the particular characteristics, as Felix mentioned, is you have a variety of devices with varying needs, networking needs, from varying levels of bandwidth to latency to some communication flows are essentially pole response, so they're from the head end towards the devices, but some emerging use cases require peer-to-peer communication within the mesh devices, and particularly for distributed control kind of applications.
Yep. And so in the mesh network, all the sensors, like we were saying, kind of both generate and repeat the signals from other mesh networks. We'll explain how the mesh forms and operates and how we form the best path of the network.
Okay, cool.
In our typical environments for smart metering, most meters will get to the router in 2 to 4 hops. But in rural environments, we've seen it go up to 20 to 25 hops. There's really no limit in terms of how the mesh can scale up.
Right. And talking about scale, some of the use cases like for automated metering, right? The scale can be thousands of meters, up to, let's say, 5,000 meters for one CGR, which is acting as the gateway router, as a Ripple border router. And we'll go into Ripple a little bit. But then, obviously, the network demand there is much lesser because these meters typically, you would query them, or they will report their metrics 4 times in a day. So the demand is less.
And it's a low bandwidth operation,
low
too,
bandwidth
right?
operation.
It's just what has to go over the.
Right.
Okay, so this is just gives you the various components of the mesh, right? So I'll start from the bottom layer, which is the endpoints, right? So what Cisco does is we have something called the resilient mesh endpoint. What that is, Cisco provides a hardware reference design, which includes the radio component and other components for the hardware module, including the BOM. But Cisco also provides the networking stack and the documentation and APIs that a partner can integrate into their own device through the DevNet, essentially Cisco DevNet. And so they can come out with variety of endpoints, and one of them is shown here, which is we partner with Itron, and this is an Itron OpenWay meter that has a CG mesh module integrated into it. There's other types of endpoints like street light sensors and line sensors and so forth.
Right. Yep. So there's a Cisco software stack running on the meter.
It looks like the one on the side of my house. Wait, did you take that off my house?
Where do you live?
Far away from here.
Is there an option to edit the counter? No.
Not by you, no.
No, no.
Since you guys are in 900 in ISM, are you seeing any interference with the like the telephones and stuff that people will have in their phone in their houses?
So it's an unlicensed band. So there's a variety of other communications. Even basically walkie-talkies and other stuff that
Maiden
utilities
monitor.
use.
Right.
So because it's unlicensed, there are interference sources. But compared to, let's say, 2.4 gigahertz, the 900 megahertz is still very less congested.
Right, so we do site surveys as well as looking both in-band and out-of-band noise. And so we also, depending on the environment, if it's near a cellular tower, we do put filters right next to the CGR for people to filter out-of-band noise. And then within the band, we frequency hop very quickly between different channels.
How wide are you using right now?
It varies, 400 kilohertz and as well as
So how wide is in how many
How
channels?
wide's your channel?
the channel.
Yeah, so that depends on the modulation. I'll come to that. But if you're using FSK, you have 64 channels there. But with the OFDM, which provides much higher data rates, we use a channel spacing of 800 kilohertz. And that can give you data rates from 1.2 megabits down to 50 kilobits, right? But the link budget that you get with lower data rates at such a wide channel spacing is much better. Right? So the other type of endpoint, and you have one on the previous version, IR509 and the IR510 here. These are particularly, these are built by Cisco. They are to address the distribution automation use cases. So distribution automation being basically, your voltage regulators, volt-var control, capacitor banks. So a lot of these distribution grid devices, 80% of them still use serial connectivity. They use SCADA protocols, DNP3 and Modbus, but they use it over serial, right? So a DA gateway essentially has, this, for instance, both of these have 2 serial ports and Ethernet as well. So you can connect the DA gateway to like a recloser control, and it has the mesh radio built into it, right? And so you can essentially enable that grid device with communications, right? Obviously there's other types of grid devices that have Ethernet and speak IP and use SCADA protocols over IP. The same DA gateway can carry the IPv4 as well as IPv6 over the mesh network, right?
Yeah, there's different security implications when you take it from serial to, packet at that point.
Right.
And so there's very different paradigm at least for the SCADA side of it.
Yep. So once the serial protocol is transported over the IPv6 network, it basically terminates in the head end where it can, the SCADA system, like the DMS system here, can communicate and control that device. Right. So we talked about the DA gateways, and we'll talk about it more. The CGR is that one there. It's a ruggedized IP67 router running iOS. It has a built-in BBU. It has 4 slots. So when you have mesh radio, obviously CGR takes one of the WPAN modules, goes into one of the slot. But then you have a choice of WAN technologies available: 3G, LTE, WiMAX. It has a built-in Wi-Fi.
So that's literally a iOS router.
That's
I can SSH
an
into
iOS
that,
router.
and I can manage that with Ansible or whatever other mechanism I
Yes,
want.
it has an iOS CLI runs T-Train.
That is literally hardware, yeah?
Yeah, it's full IP67, weatherproof.
It has it has GPS embedded in it for geofencing. If somebody, so this thing is put on a pole top, right?
Yeah.
So somebody can steal it and take it. So there's geofencing on it, so you get an alert on the
Can you-
FND.
Now, if you take it outside of that geofence, can you make it explode? That would be a feature request.
Right. It's got battery backup.
It's got battery backup. It can continue to operate for up to 8 hours without power.
And it's an outdoor device, so it's hardened for extreme element.
Negative 40 to plus 85.
Yeah, yeah.
So the most extreme, we've deployed this in northern Canada, British Columbia, hydro, where it has actually gotten down to negative 40. So yeah, it's
Celsius or Fahrenheit?
that's Celsius. That one's Celsius.
It also has edge compute or IOX capability. So it has a built-in guest OS that you can deploy your applications on.
Really?
Yes.
Is it just a Linux system of some kind, or?
And it's fully manageable. I'm not sure if you're familiar with the Cisco Fog Director and IOX infrastructure, but it's fully supported on the CGR.
Yeah, and then we have a compute module that
So
goes in here.
the IOX infrastructure is basically where you have an SDK where application developers can basically write to that SDK, and they get a bunch of microservices and so forth. And then they can deploy an app in the IOX Fog Director, and from that point on, the Fog Director essentially manages the complete application lifecycle and monitoring of the app, right? How much resources it's taking and so forth.
Yeah. So what I just heard is that there is essentially a device embedded in that, so I can deploy that out on monitoring a bunch of sensors on wind turbines out in the out in the cornfields and stuff. Yeah, it's probably
It's a little.
and now I have a legitimate test point in the field. I don't have to do a truck roll, so I can test sensors from the network that they're directly connected to.
Yes, I think the main idea here, I mean, it can be a variety of use cases, right?
That was the first one that popped in my head.
Yeah, but there's typically 2 or 3 use cases. One is around reporting by exception, right? You can have some intelligence embedded. And there's also aggregation of data, right? There can also be application level security that you want to do. So for instance, talking about the serial protocols, if you had a serial device connected here that had some proprietary application level security protocol built in, that could be implemented within the IOX piece here.
So you said the S word. So and stop me if you're going to talk about this a little bit later. So you've got these 900 megahertz IoT devices essentially that are critical infrastructure,
Right.
And they're using wireless to communicate, obviously, because it's 900 megahertz.
Right.
How do you secure the connectivity from the sensor to the router?
Right. So one of the maybe I should.
We have a whole slide.
Yeah, we have
Okay,
a whole
I'll
slide
wait
deck
then.
on that,
I'll wait.
actually.
We'll get there.
But just to finish up here, there's a smaller cousin of this, the CGR 1120, which is 2 slots, and
5 minutes.
okay, and yeah, go ahead.
Did you already mention Field Network Director?
Yeah, so the Field Network Director is the management solution. So it's scalable, scales up to 10 million endpoints. It provides features like geofencing, zero-touch deployment, very important because you're working with OT personnel, and essentially you take the CGR, put it on a pole top, it discovers the head end by itself, and basically goes through a self-configuration step. Right?
How does it do that discovery?
So there is essentially because each network has its own characteristics, right? So there is a personalization that's done before the network, the router is deployed. So it knows the URL to talk.
Oh, it knows where to look.
Right?
Okay. So
and then from that point on, it's TLS and SCEP for certificate enrollment, and then that's how it connects into the end.
Okay. So you do minimal pre-configuration before the deployment. The deployment is essentially zero touch. You turn it on, it knows what to look for.
Right.
Okay.
Okay.
Yeah, we're gonna have to race through some of this stuff.
Yeah.
Let's.
So I'll skip this.
Yeah, we can skip this.
All right. So this is how the field area network stack looks like. At the physical layer, you have the 15.4G, IEEE worked on the 15.4 and came out with the G amendment, which calls out the SUN PHYs, the Smart Utility Network PHYs, which are the FSK, OFDM, and the associated data rates. There's the 15.4 MAC layer. 15.4 frame is very similar to Ethernet and actually has been adopted by other technologies like Zigbee and so forth, right? Then you have the 15.4e MAC amendments. This really helped bring in some of the features that were needed to basically adopt it better within industrial environments. Things like frame security, extensible frame security, extensible information elements. 6LoWPAN, really important. This is the adaptation layer for 15.4 to IPv6. By the way, the fan is completely IPv6 or natively IPv6 end-to-end.
So let me make a comment there.
Yeah.
It may be, and because you said the IPv6 word, and I don't
Sure.
never miss an opportunity to talk
Yeah.
about that. So a lot of folks may not be familiar with the fact that a lot of the smart grid stuff is all native IPv6 stack.
Right.
So there's a huge deployment of that, whether it's public or not is sort of irrelevant, but the communication protocols for a lot of these, because there's so many of them, have had to move to the V6 stack.
Some of our biggest networks, they're running 2 million meters. They're all native IPv6.
Right.
2,000 CGRs and pole tops.
It's a scaling issue, really.
Yep. So 6LoWPAN, the other important point about, because it's a low-speed network, with your 40-byte IPv6 frame, there's header compression that's specified as part of 6LoWPAN. There's fragmentation and also optimizations related to neighbor discovery. These are some of the areas where Cisco led these standards and got them into through IETF. There's also, for security, we make use of .1x and 11i. And there's some minor changes to that to adopt it better for mesh networks. There's also, with IPv6, you get the IPv6 addressing. Each node has an IPv6 global address, routing, multicast, QoS, all of the IPv6 features. One particular thing which is a direct contribution of Cisco's innovations over the last many years is Ripple. Ripple is the routing protocol for low power and lossy networks. And basically, Ripple was, some of the guiding principles around Ripple were to minimize communication within the routing protocol itself, right? And still be able to dynamically adjust to the dynamic link conditions, right? And Ripple essentially forms a directed acyclic graph, so basically to avoid any loops. That's the whole idea. One important metric within Ripple is ETX, which is an estimate of number of transmissions needed to get a packet from one node to the next hop. And that's a critical metric because it can actually, that one metric can reflect your latency, your throughput, and reliability as well, right? So if to transfer one packet across, you need to do 2 transmissions, right? That means you have 50% packet loss, right? And twice as much latency, right? So, so obviously on the mesh stack, you can run UDP and TCP. One particular important aspect of this is management. So we use CoAP. CoAP specifically designed for constrained applications. So IoT FND and the mesh nodes, they use CoAP for management purposes. The metrics that are sent from these endpoints are all CoAP payloads. If you want to do some administrative action on the device, that's a CoAP command. And talking about security, I might as well mention here that we make use of additional security layer beyond CoAP at application level to basically message signing of management messages, because you don't want some hacker to turn off your power supply, at your home, right? So, yeah. Okay. So what Cisco did was, beyond contributing to these standards, we formed the Wi-SUN Alliance. So Wi-SUN Alliance is similar to Wi-Fi Alliance, Industry Alliance, where you have industry vendors as well as utilities participating in it. And so the one important thing I want to highlight here is the 1.0 FAN profile, which calls out for 15.4G, 4E, 6LoWPAN, ripple routing protocol. This is all part of the standards now. This CG mesh frequency hopping scheme, and the security, the .1x and 11i as well.
Right. So we hope to get the Wi-SUN certification, first certified devices this spring.